Thank you, thank you. So today I will be talking about StarkNet data availability, past, present, and future. Let me see if this laser pointer works. I don't think so. Okay. Down? Down for laser pointer? Hello. No laser. Okay, that's okay. This one, right? Yeah. Okay, so to give you guys some context, we've lost a little bit of color on this slide, but hopefully it's still clear. We're going to kind of start with the platform of StarkNet in general, so you guys can understand why data availability matters, where we've come from and where we're going to, and why it's more efficient. So if you look at a transaction on StarkNet, it starts in a CLI or a wallet. It gets sent to the execution platform of StarkNet. StarkNet runs its StarkNet OS, which is its transaction execution engine. And then we prove it with the Stark prover. So the Stark prover is called the Sharp. You guys might have heard the Sharp. It's called the shared prover. We're going to get into a little bit more of what it does and what its functionality is. So the Sharp prover essentially proves the execution of your Cairo code, and then the verifier written in Solidity, deployed on Ethereum layer 1. You don't see the box here, but you see Solidity down here. That's the Stark verifier. It's going to verify the Stark proof. So the next really crucial piece of information is the StarkNet core contract. That's what we're going to be getting into today. Cool. So again, this is just the transaction flow. Submit a transaction. Transactions included and aggregated into a block by the sequencer. Proof is generated and submitted, and a state update is written. Okay. This is some information about the prover. You know, why are Starks efficient? Starks are efficient because we batch these things on the prover side, and we can prove all this computation in these steps and verify on-chain in a Solidity program. You know, people call Ethereum the world computer. It essentially has the compute power of a Raspberry Pi. So you wouldn't really be able to do this kind of asymmetrical Stark proving or Snark proving without this moon math that sits behind it. And that's why we can have a verifier written in Solidity. Okay, so to zoom in on the Sharp section of it, the Sharp is just a large server that's sitting in an AWS warehouse somewhere, and it gets sent Cairo jobs. Cairo is our programming language, our provable programming language, and it gets sent Cairo jobs. So Sharp is agnostic to the platform that's writing Cairo jobs to it. We'll get into that a little bit more. So when we say that StarkNet writes its Cairo execution trace to the Sharp, it's just one of many applications that does that. DYDX does the same thing, SoRare does the same thing, ImmutableX does the same thing. The Sharp prover itself is agnostic to the job being sent. This is, you guys might have heard recursive proving. This is where the recursive proving happens. This is where those optimizations happen. Okay, so we're going to talk about fact registries. So this is Cairo zero code. Has anyone here written Cairo zero code? I'm sorry if you have. Our new programming language is Cairo 1. It looks and feels a lot like Rust. Coming from a development background, it's much easier to write. There's certain low-level primitives that Cairo 1 doesn't have, that Cairo 0 did have. They're called hints. And essentially, this program needs, the StarkNet OS, which is the execution engine, needs to be written in Cairo 0 because it has hints. So if you look at this program here on the left, it's about the simplest Cairo 0 program you can have. All it does is it allocates the values 100, 200, and 300 to memory, and it increments an output pointer, and it outputs the values in an array 100, 200, and 300. So you see the program output on the right. So what is a fact? Essentially, when we have the Sharp, the shared prover, it proves the execution trace of the Cairo code, writes that proof to the Solidity verifier, and the Solidity verifier verifies the proof. But if you don't have a programmatic interface to the verifier and to the proof that's being verified, you essentially can't run any business logic on top of that. So these facts are a way to pin Cairo jobs to proofs. So you see that program hash is a deterministic program hash of your Cairo code. So essentially in the last program, if we had any character different in this program, the program hash would essentially change. And we hash it together with the values 100, 200, and 300, and we get this specific fact attesting to this Cairo 0 run. Okay, so fact registries. This is the way that we can pin the Cairo 0 execution trace to the verifier on-chain and run business logic on top of it. So we have this concept of a fact registry. We came out with this before we came out with StarkNet. This is just a way to verify certain things about Cairo code, which is a provable programming language, on-chain. So you have your Cairo code that's executed outside the context of Ethereum, your shared prover that proves it, your verifier that verifies it, and then this DApp program, this DApp contract, is running whatever you need on-chain to be verified against the fact registry. The fact now is an attestation of the Cairo execution trace that was proved. So you guys might see where this goes, right? For StarkNet itself, the core contract is the DApp contract, and all it does is check that the execution engine, the StarkNet OS, was executed correctly and proved and verified on-chain. Okay. Like I mentioned, the sharp is not context aware of what it's being sent. It just knows that it's getting sent Cairo jobs. So everything that's being sent, StarkX, SoRare, StarkNet, it's all just being proved by the sharp and verified on chain. Okay. I hope I'm not beating a dead horse here, but the StarkNet OS is just a Cairo 0 program, and the verifier is also a fact registry. Okay, so we have the execution engine, which is the StarkNet OS. The question you might have is, like we saw in the example, 100, 200, 300, what is the output of the StarkNet OS? And the output of the StarkNet OS is the state diff. So the state diff is all of the information that happened in this block to take us from state S0 to S1 that we need to recreate the state of StarkNet, L2. StarkNet is a validity rollup, which means that we can always recreate the state of StarkNet L2 from data that's been published to L1. What data is that? It's the state diff. I'm not going to go into this too much, but we have storage values that have changed in the Merkle tree. We have class hashes that have been deployed. We have contracts that have been deployed. Everything that happened on StarkNet in this block to take us to the new state. Okay. So how did we publish this data before? And again, this data that I'm talking about that's being published, which is the state diff, is being published to the core contract in Solidity on Ethereum layer 1. We just wrote it in call data. So blobs weren't available yet. Call data is available. Call data is unfortunately somewhat expensive. We just write that big programmatic array of call data to the update state function. Now, the on-chain data hash here is the fact. It's the fact of the StarkNet OS run. So now we have the programmatic interface to the verifier. We know that for this run of the StarkNet OS, it has been proved by the sharp, and we have that information on-chain. Okay. This is just that in code. Does anyone write Solidity here? Okay. You'll see that it down here on the lower part it says require iFact registry verifier is valid sharp fact. So that's our Solidity contracts that handle the state update. Okay. So where are we at today, at least on testnet? So on testnet, there's these beautiful things called blobs. Ethereum has done a great job of implementing this KZG data commitment. And now we have the ability to commit blob data to Ethereum, and it's massively more cost effective. So what do? We get the KZG commitment of the data. That data is still just the state diff. It's just the state diff, same as we did before. So we take the KZG commitment as an input, we interpolate the state diffs and compute the hashes, and then we, after the proof verification, nothing has changed on the sharp side. So sharp prover to verifier, nothing's changed there. We make sure that the blob with the commitment was stored on the contract. Massively optimized for cost, takes our operational costs down by, I think, like 80%. What does that look like in code? Now we're no longer submitting the fact. We can interpret the fact in the code. We're submitting the KZG proof of the commitment of this state diff. Won't go into that since we only have one Solidity dev here. Okay, so that's where we are now. That's what blobs have. That's the doors that blobs have opened for us. So where do we go from here? Volition. Has anyone here heard of Volition before? Yeah, okay. So Volition essentially is a hybrid world where before we had a validity rollup where you could recompute the state of layer 2 from data only published to the layer 1. Volition is a bit of a different paradigm. We have a contract that can potentially read and write from storage, but can be specified on or off chain. There's some cool things that we have here because we have control over the programming language and the VM. We're hoping to enable developers to be able to do this in a keyword. So essentially, as you declare your storage variable, you can declare it either on or off chain, which is pretty amazing. Under the hood, low-level changes, the StarkNet OS, the transaction execution engine, records the write to the specified area and eventually commits it when proving. So there's two paradigms that we could essentially do. We could embed the off-chain state root in the global root, or we could do offline storage commitments per contract leaf. That kind of gets into a hairy technical detail. But if you'd like to be involved in this kind of Volition description, talk to me after. We have community proposals called SNPs. If you live in this world, I'd love to hear what you have to say about it. And then the final thing that we want to employ is customized layer 3s. So basically, if we can take the exact same concept but extrapolate it one layer up. So everything that was written in Solidity is now written in Cairo. So you'll see the analogs down here. The verifier contract is the same verifier business logic, but it's written in Cairo instead of Solidity. The core contract here is the same thing. It's going to handle an update state, but it's going to be written in Cairo. But what it gives us is the ability to do some fun things. So we can essentially post our state diff instead to, in blobs, in blob data. We can post it to things like Celestia. We can post it to things like Avail. Celestia specifically has a bridge called BlobStreamX that allows you to prove data commitments to Celestia. So now we have a BlobStream StarkNet contract written in Cairo that essentially allows us to have the same security guarantees by using Celestia, massively reduce our costs. So one thing that has changed in this architectural diagram is the proving service. So right now, Sharp is specific to StarkWare products. We have a couple different initiatives in the ecosystem to essentially take the stone prover, which is the heart of the Sharp, and extrapolate it so that it can prove anything sent to it. And so you talk to me after this if you want to know more about kind of extrapolating the Sharp outside of just StarkWare products. Essentially, that is it.